Here we have an ideal spring or a Hooke's Law spring. It's compressed by 10 centimeters after a 50 Newton force has been applied to it, and then shoots up a 20-gram marble straight up in the air. What's the maximum height above the spring that the marble reaches? So what this looks like in practice is our ground is here. We have our spring like this. It's compressed 10 centimeters down. There is some mass on top that gets projected this way. So this is again essentially a conservation of energy problem. So we're going to start off by looking at how much energy it has when it starts off, and then how much energy it has when it reaches maximum height, because that'll help us solve. So to start off, we're looking at the total energy at the beginning. So we have three possibilities here to work with. We have our elastic potential energy, we have our gravitational potential energy, and we have our kinetic energy. We're going to assume that when the spring is compressed, it's compressed right down to the ground. That means our h is 0. That means there's no gravitational potential energy. And of course, since there's no velocity, there's no kinetic energy. So we're left simply with our elastic potential energy, which is 1 half k x squared. Recall that the force is equal to kx, so we can then substitute some information in here. So instead of k, we have f over x times x squared. Those will cancel, and we're left with 1 half fx. Given our problem, we've applied 50 newtons of force. That's going down, so it's negative 50 newtons of force. And it's compressed, so that is, instead of 10 centimeters, negative 0.10 meters. We can solve this and find out that when we're starting off, we have 2.5 joules of energy to deal with. So that was at the beginning when it's been compressed. At its maximum height, that's the second set of energies we're going to look at. We have ET equals our elastic potential plus our gravitational potential plus our kinetic energy. So of course, at its maximum height, after it's been released from the spring, there's no elastic potential energy. And when an object is at its apex or its max height, it stops just for a second. So at that moment, there is no velocity, which means there's no EK either. We know the total energy from the previous calculation, so we know we have 2.5 joules to play with, and we know our EG is simply the mass times gravity times height. We can rearrange this to solve for the height. So the height is going to be equal to 2.5 joules divided by the mass. 20 grams is the same as 0.020 kilograms, and gravity is 9.8 newtons per kilogram. Now remember that this height is going to be the height above the ground. We need to keep in mind that we have a 10 centimeter spring. So whatever answer we get here, we're actually going to subtract 0.01 meters from my final answer, and this is going to leave me with 12.7 meters.